Bom, isto é só assim, né? Zoom, eu vejo agora que vais para o Zoom e está feito, né? Mas se tivesse lá claro. É preciso, não é preciso pôr, né? Okay. So it should be. É melhor para dois ecrãs, tu estás a duplicar, não estás a estender. Eu deixei como estava. É que ele está a duplicar. Como assim? Não tinha que passar os dados, não consegue passar os dados. Agora leva isto para o outro lado. Sim, sim, sim. Não se vai assim, né? Não. Vamos para o screen. Não, tá bom. Carrega. Carrega ali só para ficar só um, que é para ficar só quem está a falar. Isso mesmo. Assim só quem está a falar. Está aqui só o microfone está onde é coisa. Está tudo. E a câmera? A câmera também está. Não, que foi já dele. Sim, não menos a nossa. Aqui. Okay. It should be.
Okay, Fabrizio, you're going to start.
Should I start?
Yes.
Yes.
Okay, thank you very much. So, welcome to the course on IR meets data mining, machine learning, and natural language processing. My name is Fabrizio Sebastiani, and I will give this course with my colleague Alejandro Moreo. We are both from the National Council of Research in Italy, and quite uncharacteristically, we'll give this course part in presence, since Alejandro Moreo is with you, and part remotely, since I haven't been able to make it to Lisbon, unfortunately. So what about the topic of this course? Okay. So up to now, especially yesterday with the courses by Norbert Fur and Nicola Ferro, you have seen essentially what we might call core IR. So core IR defined as something that involves a query that basically translates into words and information need, and consists in trying to obtain a ranking of documents. Okay, so today, actually, we won't see core IR. We won't even pronounce probably the words search and query. So it will actually deal with a number of tasks that have to do with information seeking and let's say providing information to users, but tasks that sometimes we don't consider to belong to core IR, but that lie somehow at the intersection, at the interface between IR, data mining, machine learning, NLP. Okay, and there are several commonalities between these tasks and information search, as you have seen yesterday. So one commonality is they allow users to access and benefit from information of a non-structured type. And by non-structured we mean either text or images or video or music, etc. Something different from, say, tuples in relational databases. Although, today we will mostly deal with text, while some of the tasks that I'm going to talk about actually can be applied to other media too. Text will be the main medium I'll draw my examples from. So another commonality with search is that these tasks tend to be either tedious or expensive, or time-consuming or difficult to carry out manually, so that we might want to devise solutions which are either automatic or semi-automatic, and that will involve typically a combination of machine learning and automatic content analysis. So you have seen some examples of automatic content analysis yesterday with Norbert's lecture, when he has spoken, say, of TF-IDF. Okay, so TF-IDF is certainly, a technique for doing automatic content analysis, for extracting content out of raw media types. Okay, so let's look at the plan of today's lecture. So I will start with discussing text classification. I would say that text classification is the mother of all tasks that involve automated content analysis or textual analysis and machine learning. And the reason why I'm introducing it first is that many of the tasks I will talk about later are going to either require text classification technology, or they might be seen as sort of applications or instantiations of text classification. So part one will really be the fundamental part, and it will be split in two parts. I will start, with a part on doing basic text classification via so-called classic machine learning, and Alejandro will follow with a part on advanced text classification via deep learning. So the other four sections will be devoted to, other tasks that are sort of derivative on text classification. I will talk about authorship analysis in section 2. Alejandro will replace me by talking about cross-lingual text classification. I will start again talking about sentiment analysis. And finally, Alejandro will finish by talking about text quantification. Actually, I must say that this is a very, let's say, ambitious plan. We hope we'll be able to cover them all, although, we might have to cut down on some of the material of the later tasks. So this is, in a sense, a conceptual model of what we're talking today, with text classification being the father or the parent, or the mother of all of the other tasks. Okay, so both sentiment analysis and quantification, cross-lingual classification, authorship analysis being seen, as derivative, as using technology from text classification. So let's start about text to talk about text classification. By the way, you are certainly welcome to interrupt me should there be parts you don't understand or what. Okay, so we all like interactive classes, so please do stand up in case you don't understand something. So what is text classification? So the idea is, as I said, that many text analysis tasks can be framed as classification tasks, which essentially means as the task of predicting to which among a predefined set of groups a data item belongs to. So a data item here will typically be a text, we'll sometimes call it a document, and by predicting sometimes means, it sort of means guessing to which among these groups the text belongs to. Sometimes in the literature we speak of predicting or hypothesizing, decising, Well, I'll often speak about prediction, And these final set of groups are typically called classes or categories. Okay, so in a sense, a classification is a task of pigeonholing, taking items and putting them in the right boxes. So classification, from a mathematical point of view, is formulated as the task of generating what we might call either a classifier or a model or a hypothesis. So essentially, this hypothesis or classifier is typically denoted with letter H, and it's a function that takes a domain of documents. Here, data items in general, but in our instantiation, textual documents. So it takes a domain of textual documents, and maps each document into a class belonging to a finite set. So this finite set of classes is typically called the classification scheme or the code frame. I will typically use the word code frame. So, there are many instances you might think about, that are instantiations of text classification. So suppose you have to assign newspaper articles to the page where they should appear in the newspaper. So a certain document should appear in the home news page, in the sports page, or in the lifestyles page. So deciding which is the correct page, is a classification exercise. So one typical task, which is very used in many scientific disciplines, is assigning subject codes from a predefined taxonomy to scientific papers. So you have computer science papers, and you need to assign subject codes, from the ACM classification scheme. So the ACM classification scheme is here the code frame, and it's a hierarchical classification scheme. So partitioning emails into legitimate and spam, what we typically call spam filtering, So this is an instance of binary text classification, since you have just two, classes, Again, coding textual answers returned to open questions in questionnaires. Okay, so sometimes you might want to run a questionnaire that includes open questions, and if you have many such answers, you might want to use a classification system to assign to, let's say, one code or the other. Say one code could be, happy with the quality of the website. So this might be one code, or unhappy with the economic conditions of the credit card. So this may be another code, So this is typically what survey specialists do, and this is called survey coding. Okay, so coding the textual answers returned to open questions in questionnaires. So in sentiment classification, we sometimes want to mark a textual comment, say on a product or on a political candidate, on a policy, as conveying a positive or a negative opinion about its subject. So this is called sentiment classification. And also authorship verification is something that we will touch upon in the later part of the course. This has to do with detecting, say, whether a suspect is the author of an anonymous text or not. Okay, so if the suspect is John, so our code frame is John or not John. So you see that there are really thousands potential applications of text classification, because classes, or categories can be just about anything, So it really takes, your fantasy to formulate something as a text classification exercise, So the question we will be asking ourselves is, can this classification be automated? Can we build tools, that maybe semi-automate this? That means that support the work of humans who need to actually classify text manually, So these problems, share several characteristics with other problems in IR. Okay, so typically, unlike other types of data, such as factual data, data from tuples in relational databases, numerical measurements, well, text require subjective interpretation. That means that all of the above tasks, pretty much like search in IR, are non-deterministic. So it's there is no algorithm that can exactly obtain 100% accuracy in solving the task. And one of the problems with text is that really the variety of linguistic devices that we as humans use in order to convey what we mean is really bewildering. So it's a text is very much non-standard. Okay, so because of this, it provides many variations that need to be accounted for. Also the fact that different people use different variants of language, so that language use differs across people, inserts an additional level of difficulty. And also the evolution of language is an additional level of difficulty. This basically means that, programming as it was done in the old times, programming if-then rules that automatically classifies text is difficult. If-then rules, where, rules such as if the document contains words Viagra or contains the words chalice, then classify it as spam. This is an if-then rule of the type that used to be manually programmed, in the text classifiers of the old times. Okay? But this way of solving the problem is difficult, is bound to lead to software characterized by low accuracy because it cannot account, for the variety of linguistic devices that I was mentioning above, for the language use, which is different across people, for the evolution of language, etc. It's also a way of solving the problem which is not economic, because creating a text classifier is very expensive, but also maintaining a text classifier is very expensive, meaning updating in order to answer to potentially newly arisen problem. And it's also an endeavor which is too slow for fast emerging needs. So this way of solving text classification by if-then rules, was something which was used in the 80s and which has been really replaced by the, let's say, the supervised learning approach, which is essentially based on a single idea. Okay, so the idea is to set up a software that learns to carry out the task, from training examples, from what we call training examples, which mean examples in which the task is being performed correctly by competent humans. So a typical example is assigning subject codes from a predefined taxonomy to scientific papers. The idea here is, the software learns to do this by looking at papers, at a set of papers which have been provided to the system as input and whose codes had originally been assigned by experts. So the basic takeaway message, the consequence that this software must try to understand, the characteristics that make a paper suitable for assigning it to a certain code. So trying to, in a sense, understand the correlation between the characteristics of the text, and the code which has been assigned to this text. Okay? So this is the core idea behind supervised machine learning, and I believe that most of you have already encountered supervised machine learning in one way or the other. Okay, so in this course I will try to be very introductory, also with the goal to cater for those of you who are not terribly familiar with this technology, but so I'll try to, to convey content for the uninitiated and try to convey also content for those of you who are more advanced. Okay, so in a sense, this course is about formulating text analysis tasks in terms of text classification, and using machine learning technology to design, to implement, and test the resulting text classification systems. So this is the structure of this first part, and now let me go and discuss the relationship between supervised learning and text classification. Before this, I'll give you a few definitions. Okay, so in general, classification is what we might call a ubiquitous enabling technology in data science. So it's studied in many different fields, including pattern recognition, statistics, machine learning, and the like. So here we will see one instantiation of it, which is the instantiation devoted to dealing with text. And one key aspect of classification in general, is that the membership of data item into a class must not be determinable with certainty. For instance, if we have to predict whether a natural number belongs to odd or even, or whether a natural number belongs to prime or non-prime, this is not classification, because these can be solved deterministically. Classification always involves a subjective judgment. Okay, and text classification is essentially the instantiation of classification where data items are textual, and the text can be of pretty much every type, news articles, treatises, emails, sentences, questions, queries, tweets, product reviews, whatever, and also, partly textual items are also counted too. So for instance, web pages are partly textual because they tend to contain content of many different types, including images and links, etc. So there are several different types of classification. So I'm reporting here the main four, and these mathematical definitions are important to understand the rest of the course. So binary classification is the easiest type, and basically it means classification when I have to distinguish just between two different classes, C1 and C2. So email filtering is a typical case, because this has to do with assigning emails to one of spam and legitimate. Spam and legitimate, relevant or not relevant, noise or signal, all of these are examples of binary classification. So single label multi-class is a very important type, and it has to do with the cases in which the code frame has more than two classes. Okay, so we always need to assign each document to one and only one class, and this is the meaning of single label, but where the classes have to be drawn from more than two classes, and this is the meaning of multi-class. So assigning news articles to one of home news, international, entertainment, lifestyles, etc., is single label multi-class. So multi-label multi-class is slightly different. Okay, so again, here we have more than one class, but here the idea is that we should, in a sense, each item may belong to 0, 1, or several classes. It doesn't have to be, it doesn't need to belong to exactly one class. Okay? So the case of, say, assigning computer science articles to classes in the ACM classification scheme is one such example, okay? Because we typically want to assign each article to several, such classes, to several specialized terms in the thesaurus, And multi-label multi-class may be typically solved as n independent binary classification problems. So for each of the classes C1, Cn in the code frame, we may set up a binary system that decides whether our textual item should be assigned to C1 or not, to C2 or not, to Cn or not. Okay, so n independent binary classification decisions. So ordinal classification is different. So ordinal classification is as in single label multi-class. So we have n classes with n higher than 2. We need to assign to each document to one and only one class, but the difference is that the set of classes is typically ordered. One example is, say, assigning product reviews to one of disastrous, poor, so-and-so, good, excellent. Okay, so assume that you have to read a textual comment, that presents opinions on a certain restaurant, and you need to decide whether this textual comment basically claims that this restaurant is disastrous, is poor, or say is excellent. So this is called ordinal classification. So an important difference is that the definitions above denote what we might call hard classification. So hard classification basically means take a textual item and assign it to one class. Okay, but you can, in a sense, come up with a softer definition of classification. So soft classification essentially denotes the task of, let's say, returning a score that is between 0 and 1 for each pair, consisting of a document X, and a class C. This score essentially denotes the probability that X belongs to C as, as estimated by the classifier, or the strength of evidence or the confidence that the classifier has in the fact that X belongs to C. So typically a probabilistic classifier returns such a score. And in this case, it is, noted in this way, and this is called the posterior probability, which is read the probability that X belongs to C. And of course, it belongs to 0, 1. So sometimes, some type of classifiers return scores which are not in 0, 1, which cannot be interpreted as probabilities. So AdaBoost is such a classifier, is such a learning device, and it returns essentially confidence scores which are any real values. Okay, and in these cases, it is often the case that we want, to convert these confidence scores to probabilities which are in 0 and 1, because for a variety of reasons, as we will see, it is sort of convenient to have posterior probabilities that range between 0 and 1. And this conversion can be done via the so-called logistic function. Okay, so via a method called classifier calibration that essentially converts the outputs of a probabilistic classifier or a non-probabilistic classifier into probabilities that belong to 0 and 1. So this is an example of the logistic function, but I will skip it for the moment. Okay, so what are the relationship between hard classification and soft classification? Well, in the binary case, hard classification often consists of first training a soft classifier that returns scores, scores that we assume to be in 0, 1, and then picking a threshold t, such that if the score is higher than t, this is interpreted as predicting C1. If the score is smaller than t, this is interpreted as predicting the other class, C2. So this threshold is typically picked via parameter optimization techniques, and in soft classification, the scores that are returned in this way, these scores of type SXC or the posterior probabilities, they can be used for ranking. Okay, so we are coming back to ranking that you saw yesterday. So the idea is that given a class, you might want to rank the items for that class. Okay, so where the top ranked items are the ones that are most likely to belong to that class, But you can also rank classes for a given item, So where the top ranked classes are the classes that are more suitable to classify that item. So once you have soft scores, you can do quite a lot. What is the difference, the main difference between hard classification and soft classification? The main difference is that hard classification is used for fully autonomous classifiers, while soft classification is used for interactive classifiers. So classifiers that have humans in the loop, that have humans that are in charge of taking the final decision. So for instance, a spam filtering system is typically implemented as a hard classifier, okay, because that spam filtering system autonomously decides whether a certain message is legitimate and should be sent to the mailbox of the user, or whether it's spam and should be sent to the spam area, to the spam filter. Typically, there are other applications, maybe applications which are more critical, let's say, where, a human wants to have the final word, So, a soft classifier is used for ranking, say, the items for a given class, so that it's more cost-effective for the user to perform the final classification himself or herself, by scanning the ranked list from the top. So soft classification for humans in the loop, hard classification for fully autonomous classifiers. So something that is quite important to understand is that text classification may be performed according to several dimensions, okay, that we will sometimes call axes and which are independent of each other, okay. So the examples I have, let's say some examples I've used up to now are examples according to topic, classification by topic. So one example I used was, say, classifying news, classifying news articles in terms of the page they should be printed in. Okay, so classifying a news article in terms of whether it is about sports or not. Okay, whether it's about home news or not, whether it's about politics, whether it's about lifestyles. This is called classification by topic because it has to do with the topic of the text. Classification by sentiment is a completely orthogonal dimension. Okay, so different texts might be about different topics, but here we are not looking at topic, we are looking at the polarity of the opinion which is expressed in the text. Okay, so a text might be a product review about a camera or about a movie or about a book, but here we are interested in the fact that the product review is positive or is negative about its subject matter. Classification by author is yet another dimension, which we'll be looking at. So here the authors, the different candidate authors for a text, an anonymous text, for instance, are the different classes, or by native language. Okay, so you might want to figure out what is the native language of the author of a specific text. Okay, whether a text written in English was actually written by someone who is English, or maybe by a French guy, by an Italian guy, or by a Swedish woman, So this is very useful in areas such as in philology, forensics, cybersecurity, and we will come back to this. So all this to say that there are different orthogonal dimensions according which we might want to classify text. So let me come to the core of the discussion, supervised learning and text classification. As we said, we are going to look at an approach in which a generic learning algorithm, say a sport vector machine, is used to train a classifier from a set of manually classified examples called the training examples, okay? So that the classifier learns from these training examples the characteristics that a new text should have in order to be assigned to a certain class. It learns the correlation between the characteristics of the text and the classes that should be assigned to it. And as I said, the advantages that are that annotating or locating training examples is much cheaper than writing classification rules. Okay, so it's much easier, say, to locate or to point, one to a set of red objects rather than writing a rule that allows us to understand whether a certain object is red or not. And also, one advantage is that there is this allows for easy updates to changing conditions. Say you have to add new classes to the code frame. You need to delete old classes, existing classes from the code frame. Or maybe you need to split one class in two subclasses, Or maybe, some existing classes, have a sort of a shifted meaning. The meaning has changed. What you need to do in all of these cases is just provide new training examples which reflect the new situation that you're interested in modeling. So this is, in a sense, a graphical depiction of the workflow, of a text classifier. Essentially, what you do is you start with training document. You start with a classification scheme, a set of classes, and training documents manually annotated according to this classification scheme. What you need to do is to pass these training documents through a content extraction phase. And the content extraction phase essentially maps a raw document, a document in raw form, into a form which you already know. You have probably already guessed what it is. It's a vectorial form. You have seen vectors yesterday in the Norbert Fuhr's introduction. So it maps a training document into a vector, into a form that the classifier, can understand. So the same content extraction phase is used for mapping unlabeled documents. So the documents that you want to classify. So the unlabeled documents, together with the trained classifier, are fed to the document classification phase, which essentially takes the trained classifier, takes the unlabeled documents, and returns these unlabeled documents with a label on it, so in the form of classified documents. Here, I'm representing a sort of what we might call an optional phase, which we call validation. In the validation phase, a user might want to take a look at some of the classified documents, check whether the labels assigned are reasonable or not, are correct or not, and especially in the cases, in which these are incorrect, well, correct these labels and feed back to the classifier training phase the corrected documents. Okay, so all of the documents that have been checked by a human, are fed back to the classifier training phase, which can retrain the classifier using this time an augmented set of an augmented training set, the original training documents and the documents which have been validated. And the idea is that the classifier that will be trained in this phase will likely be more accurate than the one before, especially in the areas, especially on documents similar to the ones whose label has been corrected, has been replaced by the correct one. So let me look at the content extraction phase. So some of the parts that I'm talking about now, you have already seen them yesterday while in the Norbert Fuhr's classes. Okay, so the idea is that we need to convert the text into vectors in a common vector space. The idea is that these dimensions of the vector space are called terms. Terms is typically IR terminology. In machine learning terminology, we call them features. In statistical terminology, we call them covariates. And the number k of features which are being used is called the dimensionality of the vector space. So in order to generate vector-based representations for documents, what we need to take the following steps. Okay, so feature design and extraction and feature weighting. I will skip I will skip feature synthesis because of lack of time. Maybe I will touch on feature selection. And I will use the following notation here, where the set of documents is partitioned in a set of labeled documents, which are training documents. The unlabeled documents that are the ones that need to be classified. So here is a familiar Cartesian plane. Here I'm essentially recalling notions that you have probably seen yesterday. So if we have chosen our features well, and this is a very simplistic example in which we have only two terms, T1 and T2. If we have chosen these terms well, it will probably be the case that vectors representing documents, belonging to a certain class will be close to each other. Here we are talking about, in this graphical example, we are talking about 4 different classes: the pluses, the stars, the sharps, and the ats, represented by these 4 graphical symbols. Okay, so here, in a sense, if we have chosen our features well, data items belonging to the same class will tend to be close to each other. And this is the case represented here in this graphical depiction. Essentially, trying to training a classifier, means trying to detect what we call a separating surface, which is here represented by a line in the two-dimensional space, a plane in three-dimensional space, and in n-dimensional space, we often talk about a hyperplane. So here, essentially, we are seeing, let's say, a classifier, a binary classifier that distinguishes, the sharps from everything else, And you see that this is a perfect classifier that essentially perfectly separates the sharps from anything else. Okay, so we say that these data are perfectly separable from by a linear classifier. So the idea is that once you have trained this classifier, once you have a new document, which is here represented as a red dot, well, you map it into a vector. This is the location of the new vector, and basically what you do is you check on which side of the hyperplane, on which side of the classifier this lies. So here you will basically, you're predicting that this new document belongs to the sharp class and doesn't belong to the others. Essentially, the task of a supervised learning system is not only to detect a classifier, but to choose the best possible classifier. Something that you might notice here is that we have exactly the same training examples of the previous graphical depiction, but the difference is that two different lines have been chosen. The first one was a straight line, and the second is a curved line. So different learning methods tend to choose different types of classifiers. Okay? So the classifiers, that choose, so the training methods that choose classifiers which are straight lines or let's say flat hyperplanes or the like, are called linear classifiers. Okay, so feature design, as I said, has to do with choosing the right features for your problem. And in classification by topic, a typical choice is to make the set of features coincide with the set of words that occur in the training set. Okay, so we won't use the ones that do not occur in the training set because otherwise, we will not be able to infer any correlation between them and the classes. And as you have probably seen yesterday, this is typically preceded by phases such as stop word removal or stemming or lemmatization, because all of these are meant to improve efficiency and to improve statistical robustness. I will not repeat these because I'm pretty sure you have discussed this yesterday. So the dimensionality K of the vector space that results, is the number of features you have chosen, the number of words, the number of stems, the number of lemmas that typically occur at least once in the training set. And this can be a very, very high number. So even for a moderately sized corpus, it can be in the order of tens of thousands. Okay? Well, the problem is that each document usually contains much fewer than tens of thousands unique words, especially if it is a short document. So if we do indicate the absence of a word from a document by 0, the consequence is that these vectors are sparse. Sparse means that many items, many cells in these vectors are 0, And this is one characteristic of representations of text, So in a sense, vector sparsity, so containing many zeros, and high dimensionality, so being very long vectors, are the two most important characteristics that distinguish text classification from other instantiations of classification in data mining. So in many other applications of data mining, you don't have high dimensionality. You have maybe 300 features, 100 features, 20 features, but you don't have features in the thousands, So this is very characteristic of, non-structured media, and text in particular. And vector sparsity is always a characteristic, is also a characteristic of text. Okay, so in many other data mining endeavors, the vectors are shorter, but the vectors are also dense. Okay, so you don't find cells which are, or a high percentage of cells which are zeros. Okay, so vector sparsity and high dimensionality are the most important characteristics that tell text classification apart from other instantiations of classification. So here I have examples of what unigrams are and bigrams are, but I guess that you have gone through them yesterday, so I will skip them. Something I want to mention is that alternative representations for text are formulated in terms of character n-grams. Okay, so a character n-gram is a sequence of n characters that appears in the text. Here we have an example of character 6 grams, sorry, not 5 grams, which are essentially sequences of characters as they appear in the text. And these kind of representations are very popular, especially when we need to classify corrupted text. Okay, so text which includes lots of noise, such as text resulting from optical character recognition, or text from social media, where there is a high percentage of typos, And the reason is that, when you have highly corrupted text, you tend to find many words which are not, which do not belong to a regular dictionary. So you might find a typo, so that the word computer might be misspelled as computer, And so, when you have a high percentage of typos, this increases the vocabulary size and decreases the number of matches, So for instance, a text that contains word computer and a text which contains word computer have nothing in common, And this is a problem, While if you use representations based on character n-grams, well, there is quite a lot in common. There is, for instance, a sequence of characters such as computer, And these set of character n-grams, are often enough to recognize texts as similar, even if they contain a high percentage of typos. Okay, so for all these applications, using character n-grams is quite popular. Let me go talk a bit about feature selection. Sometimes the fact that the dimensionality of the vector is very high is a bit of a problem, because you might run into so-called overfitting problems. Okay, so overfitting is the situation in which you have a too large dimensionality for vectors and too few training examples. Okay, and so if you need to solve this overfitting problem, you might want to do some feature selection. So cut down on the dimensionality of the vector. A typical approach for cutting down on this dimensionality, which is called feature selection, is to try and compute a function like this. MI stands for mutual information. The mutual information between term TK, so feature TK, and class CI, And it means essentially trying to understand whether there is a high correlation or not between a certain term and a certain class. Say, if the term is athlete, and the class is sports, sure, there is quite a high correlation. And mutual information will typically return a high value, Instead, if there is a very low correlation between between, such as, let's say, the term man and the term sports, in this case, mutual information will return a low value. And the idea of feature selection is trying to retain all of the terms for which mutual information returns a high score. So there are lots of such formula. Mutual information is one possible function, another is chi-square, another is information gain. So all of these functions, I'm not going through the mathematical formula here. All of these functions try to detect the amount of correlation between a feature and a class with the goal of retaining only the features that have the highest amounts of correlation. Feature weighting, I will just say a couple of words here because you have encountered feature weighting here. I'm pretty sure you have talked about TF IDF, for instance. So the idea of feature weighting means attributing a certain value to the presence of a feature in a certain vector. Okay, so this weight basically means how important that feature is in the for that document. You can have binary feature weighting, just representing presence and absence in terms of zeros and ones, but numeric is the most frequent case. And something you haven't seen yesterday, you have probably seen unsupervised ways, of doing feature weighting, such as TF or IDF or BM25. Sure, they can be used for text classification too, but in text classification you can also use supervised term weighting, because in a sense here what we have is training data. So for instance, we can replace IDF with mutual information, so that in a sense mutual information will in a sense encode a much more interesting and meaningful notion of the document independent importance of a certain term. Okay. So classifier training, So I will not spend much on this because that's essentially the domain of machine learning. And if I had to spend time, in introducing specific classifier training algorithm, I will probably have to cut down on much other interesting content. The idea is here that if you want to do binary classification, essentially any supervised learning algorithm can be used for training a classifier. I'm pretty sure that most of you have encountered in one form or the other some of these supervised training algorithms. Support vector machines, boosted decision stumps as represented in AdaBoost, logistic regression, naive Bayesian classifiers, which are a very easy, a very simple form of probabilistic classifiers, and lazy learning methods, such as nearest neighbor based methods, such as KNN. So all of these choices are fairly popular in text classification. I would say that support vector machines and logistic regression are probably the most popular. Naive Bayesian methods tend to work less well, and one type of method that is not very popular in text classification, although it is popular in other fields of data mining, is boosted decision trees. Okay, so these are not very popular here. They tend not to work terribly well on text. Well, there is this famous so-called principle or theorem called the no free lunch principle, which basically says that there is no single learning algorithm that can outperform all other algorithms in all contexts. So in a sense, this means that whenever we have a concrete problem, we should do experimentation, in order to figure out what is the best method, but also, that we should look at, what other people in the literature have found about other methods. Okay, so what we should remember is that implementations of supervised learning should cater for the very high dimensionality typical of text classification and the sparse nature of the representations involved. So when we move from binary to single label multi-class, again, the very same methods can be used with the proviso, that if we want to use SVMs, there are specific implementations of SVMs that cater for single label multi-class, because SVMs are the only algorithm among the ones that I have mentioned that are not natively multi-class. They are natively binary. So cascades of binary SVMs need to be used in order to do single label multi-class classification. Instead, if we want to do ordinal classification, again, we need to use completely different algorithms. And here I've listed a couple of examples, Zvorim and Zvorex, which are, again, different types of cascades of binary SVMs. I have a slide here about parameter optimization. You might have encountered parameter optimization before. So the idea is that many of these supervised learning methods actually depend on some parameter. And in order to obtain high accuracy, from these classifiers, it is important to optimize these parameters. So one example is the C parameter in soft margin SVMs, which trades off between the model complexity and training error, and other parameters there for nonlinear kernels, but also other methods actually have several different hyperparameters. They are more accurately called. So these hyperparameters need to be optimized, and one typical method for doing it is k-fold cross-validation. The idea of k-fold cross-validation is that what we do is we split our training set, to say, in 4 here in this figure, and we run several experiments with several different choices of the parameter, So for instance, we run several experiments where this first portion is used as the test set, and this portion is used as the training set. And we run several runs of this experiment 1 with different choices of different numerical choices for the parameter we want to optimize. We redo these for experiment 2, experiment 3, and experiment 4, and the result is that we have actually classified all of the data set in 4 different portions, in 4 different experiments, for all different choices of the parameter. And once we have done this, we can compute the accuracy we have obtained, and we can pick the value for the parameter which has returned the best accuracy. So this is called k-fold cross-validation. It is a very fundamental technique for doing parameter optimization. So I have used more time than I had expected, which probably means that we will need to cut down some content in the second part, but I want to devote some attention to how we evaluate a classifier. Yesterday with Nicola Ferro's lecture, you have seen quite a lot about the evaluation of ad hoc search, of core IR algorithms. Now I will add something about the evaluation of classification algorithms. So here, there are 2 important aspects that should be taken in consideration when evaluating a classifier. One is efficiency, so computational cost, and the other is effectiveness, which essentially means accuracy. So efficiency is consumption of computational resources, okay? And we should here look at both training efficiency and classification efficiency. So training efficiency is the efficiency, the computational cost that a certain algorithm takes at classifier training time, while classification efficiency looks at the efficiency of a readily trained classifier when actually classifying unlabeled data. So they are both important. Of course, what you should consider is probably the fact that a classifier is trained only once, but so in operational condition, it's applied many times. Okay, so many people consider classification efficiency more important than training efficiency. But accuracy is probably even more important. Okay, so it's probably more important because accuracy issues are here to stay. So you will not improve your accuracy by using more powerful hardware, but you might, let's say, you might improve the efficiency of your system, the computational cost of your system by using, more powerful hardware. So because of this, accuracy, effectiveness is typically considered more important than efficiency. And in order to compute effectiveness, as usual, as in IR, as in core IR, we need to carry out experiments on one or more data sets which are meant to simulate our operational condition of use. And it's once we have these data sets, it is important to decide which evaluation measure we are going to use. Okay? So you have talked yesterday with Nicola Ferro about evaluation measures, and you have certainly talked about true positives, false negatives, and true negatives. Okay? So the fact that, especially when it comes to binary hard classification, you can run your algorithm on a certain set of unlabeled data and basically partition the results into these 4 cells. So the idea here is that in classification, we try to come up with measures, with measures that combine these 4 cells into a meaningful measure of accuracy. And this measure for classification is typically F1, which is the harmonic mean of precision and recall. You have seen precision and recall yesterday, so I will not repeat their definitions, but here essentially is the definition of F1, which in a sense, tries to combine precision and recall in a meaningful way. One important fact about F1 is that it is robust to the presence of imbalance in the test set. What does imbalance mean? It means that in many applications of classification, we have very few positives and very many negatives. Okay, so you have the same in ad hoc information retrieval as you saw yesterday. And in these cases, you want a measure that doesn't reward classifiers for always predicting that the document is irrelevant. So vanilla accuracy is another measure that we will encounter, and this is not robust to the presence of imbalance in the test set. Okay, so F1 is, in a sense, specifically designed for tackling situations of imbalance. So when you, the F1, as I have described it now, essentially tackles binary classification. If you want to tackle multi-label, multi-class classification, you have to compute F1 on each individual class, As recall that we tackle multi-label and multi-class classification by repeating binary classification class by class, and the same we need to do when evaluating. In this case, there are 2 standard ways of averaging the F1 results which are computed on the binary cases, on the several binary cases. So averaging them across the classes. One is called micro-averaging, another is called macro-averaging. I will not enter these definitions because in order to not to waste too much time, but just suffice to know that these are the standard ways of evaluating multi-label and multi-class classification. In single label multi-class classification, instead, vanilla accuracy is very often used. It has this definition, and vanilla accuracy is fairly intuitive. So essentially, it's the fraction of the elements on the diagonal divided by the total number of elements, okay? Because the elements of the diagonal represent the correct predictions. So omega 1,1 represents all of the documents that should have been assigned class 1 and were indeed assigned class 1. Omega CNN represents the documents that were assigned class CN and should have been assigned class CN. So the elements in the diagonal are the correct decision. So the vanilla accuracy is the total number of correct decisions divided by the total number of decisions. And this is considered a reasonable measure for evaluating single label multi-class classification. I will not enter the problem of how to deal with ordinal classification. It has its own measure, which is called macro average mean absolute error. And it has to do with the fact that, not in ordinal classification, not all errors are equally serious. Okay, so mistaking disastrous for excellent is a very bad mistake, but mistaking good for excellent is not a very bad mistake. Okay, so different types of mistakes should count in a different way. Soft classification is evaluated differently, again, because what you need to look at, you don't need to look at hard decisions, but soft decision. And typically mean reciprocal ranking is something that can be used, where you essentially look at the rank that the correct label has been assigned to. Okay, so for instance, if you are looking at whether, if you actually look at the labels that have been assigned, predicted, at the scores that have been predicted for the various label, and you want to look at which on which position of the ranking is the label that was the correct one. So, you have seen that different types of classification tasks, binary, single label multiclass, multi-label multiclass, and ordinal, have their own mathematical evaluation measure. And it is always very important, once you apply classification on a real case, it is very important, to look at, to basically understand what the characteristics of these application are, in order to understand whether this is a case of binary classification, single label multiclass, or multi-label multi-class, or ordinal. Okay, so there are very many research papers, published by respectable researchers, where people do these kind of mistakes. Okay, so for instance, they encode a certain application as single label multiclass without realizing this should have been encoded as an ordinal one. So it's very important, to carry out this initial requirements analysis phase. Let me skip this. This is an important slide for those of you who might want to play, with text classification software, to experiment for it. So I'm putting up links to two important frameworks, environments for doing text classification that include different types of software for doing text classification. One is scikit-learn and one is Weka. Many of you might already know this. scikit-learn, the main difference is that scikit-learn is Python-based, while Weka is Java-based. Scikit-learn tends to be more complete, I would say. So it contains different classification algorithms, regression, clustering, many others, and it can interoperate with numerical and scientific libraries, including. I can hear background noise. Any questions?
Oh, the cable.
Can you hear us still?
Okay. And okay, so, these are two of the most frequently used packages, for doing text classification. I will skip the advanced topics part because I think I have used quite a lot of time, and I will leave the mic to Alejandro, that will discuss some, let's say, advanced ways of doing text classification. I guess I should stop sharing.
Okay. So in the meantime, do you guys have questions? Yeah, go ahead.
Yes, this is a good moment to ask questions, of course.
Go ahead, or maybe you can repeat the question. Yes.
Don't use mean reciprocal range.
You heard it?
It's not.
The question, Alejandro.
It was not actually a question.
It's totally flawed that we have experimental evidence that 30% of the significance tests give the wrong outcome. It's not interval scale, so you cannot compute a mean.
Did you hear that, Fabrizio, or should we repeat it for you?
Well, I seem to have heard that this is Norbert Fuhr, I couldn't understand. I heard it's a question about mean reciprocal ranking.
Yes.
It's a critique, but I couldn't exact formulation of the question or of the remark.
Do you want me to repeat it?
Yes.
Yes. He said that it's not statistically meaningful in the sense that you cannot compute the mean and
Significance tests.
and you cannot perform significant tests.
Well, yeah, I assume you are probably correct. You're probably right, Norbert. It's I would say that there is a lot of variance among different authors, across authors who want to evaluate soft classification, especially because there's not much research, I would say, on soft classification. It's other measures that are sometimes used are the Breer score, or the like, but to say the truth, I don't know whether they are also meaningful in the way you say. Okay, so admitting statistical significance testing and the like.
I'm not sharing the right screen, I think.
You have to drag it.
Yeah, the problem is that I cannot. Okay.
The bottom line is, in a sense, there is not much around about evaluating classification, especially because there are not many applications where this is.
I should not be able to share. Let me check if we are which screen I'm sharing.
So, do you think this is the time for the coffee break? I don't know. I mean, I have 50 minutes, no less than 50 minutes to match. Yes, but I have only one material.
Okay.
No, it's up to you. Do you want to?
No, it's fine, it's fine. So if think this best.
Okay, is everything set okay?
Should be, yeah. Just check.
Of course, this is not working. Okay. Okay, I'm going to be presenting this part of the lecture, which has to do with word embeddings for text classification. Okay, so the topic of this lecture is moving from this word space model that Fabrizio has explained before to a neural embedding.
Alejandro, just wait a minute. I think you're sharing the screen corresponding to a web page.
Okay.
So it's probably take this back to the place. But it's probably my connection.
So the problem is also that there is a delay.
Yeah, no, it's probably okay.
Okay, that's, I will assume that it's a problem of delay in the room.
Yeah, okay,
Otherwise,
okay,
I can.
no, it's fine.
Okay, it's fine. Okay, so as Fabrizio has. Okay. So we're moving from the vector space model, which is this vector space in which we have one dedicated dimension for every single word. And as Fabrizio has explained before, this poses many problems. So the first one is that every word is characterized by something which is called the one-hot vector, which is a vector like this, in which we have everything filled with zeros, but one value which takes the value of 1. And this dimension is dedicated to this word. So for example, the word cat. And this is a sparse vector representation that we can use to represent documents as the sum of one-hot vectors. Maybe by multiplying them by their relative importance, or for example, using a weighting criteria like TF, IDF. So the real problem here is that this space is not able to capture semantic similarity. So if you take these three examples, these three documents as example, you would realize that the differences between game and match, which should be considered as similar terms, are as dissimilar to each other as they are to Trapped. So the thing is that similar words happen to be as similar to, as close to each other as different words. And so the idea is how to better represent this phenomenon. One possible solution implies using linguistic resources, but this entails many human effort. This is costly. But there is one observation which we can take advantage of, and is the fact that just consider these sentences. So Pisa is a province of Tuscany. This is a relatively likely sentence. Red is the color of the rainbow, is a relatively likely sentence, and so on and so forth. But for example, red is a province of the bicycle is completely unlikely. And it's completely unlikely because the words do not seem to be electable when you use other words in context. This is something which is better represented by what is called the distributional hypothesis. And by quoting Firth, you shall know a word by the company It Kids. Although the distributional hypothesis is more often attributed to Wittgenstein, who said that the meaning of the words is somehow determined by the context in which every word tends to be used. So I'm going to give you a couple of sessions to read these sentences. in order for you to try to figure out what beam is. And even though you have never heard or read about beam, you have automatically inferred many properties of this word. So it's something which you can take in a restaurant, something that you can cook. It's something you can like or not, and seems to be some type of food. So the idea is that we are going to construct what is called a distributional semantic model, which is a model aiming at capturing this word meaning. And we are going to do this by inspecting the context of the words. So here are some examples of what we are going to be considering the context. For example, for cake, we're going to be considering 2 words ahead and 2 words before. This is just an example. You can consider 3 ahead, 3 before for an entire document as a context. What we are going to do is to scan as many texts as we can and just counting, keeping track of the number of occurrences. And this is one of the very first attempts in literature, something which is called the word context matrix. And it's something that looks like this, in which you have as many rows as terms you are modeling and as many columns as terms, because you use the same terms in the vocabulary to model the context. And so it turns out that if you do this exercise for quite some time, you will end up having some distributional patterns which are similar for similar words. So for example, cake, stick, or our famous beam will end up being represented by similar distributional patterns. While other words like engine will have completely different distributional patterns. And so the idea is that we are going to be using these new representations instead of our one-hot vectors, because these distributional vectors are better for representing the semantic of words. And are better because they are not orthogonal. And this is in contrast to what happened with the one-hot vectors. They were orthogonal to each other. So similar words were as similar to each other as dissimilar were. Whereas this is no longer true for non-orthogonal representations. And we have still the same problem as before. We're working in a high-dimensional and still sparse space. So the idea is that we would like to move towards dense representations for reasons of efficiency, and because we know that the basis of our vector space is no longer orthogonal. So the idea is trying to embed, and this is what embedding means, is trying to find projections, maybe non-linear, so that we move from a sparse and high-dimensional space towards a space which is dense, continuous, and low-dimensional. And we will call such a function an embedding function. And because we are working in a reduced dense space, we are forcing some words to share some dimensions in the space. But we are going to be using this to our advantage. So we are going to be using this property of the new space in order to better group or align or project words in terms of their semantic or syntactic similarities. One of the very first attempts for doing so is what is called the singular value decomposition, which is a matrix factorization technique. I'm not going to enter details, but the idea of singular value decomposition is that this factorization compress a matrix in a way that it loses no information. But in doing so, it finds the best ordering of dimensions in a latent space, so that if you were to pick only some of these dimensions, you will be retaining the most information. So for example, if our original vector space was composed by 2 dimensions, and if we want to take only one, then singular value decomposition says that this is the dimension you should take. This is the dimension retaining the most information, in this case in terms of variance. So the idea is moving from this matrix factorization technique towards neural models by just giving many texts, as much text as we can to the model, so that it makes sense of it. These kind of methods are called context prediction methods, in contrast to context counting methods. So the idea is to pose what is called a secondary task or an auxiliary task, which is something that you ask the model to solve, because you believe that for the model to be able to solve this, it has to encode some kind of semantic modeling of the words. So, for example, if you take many texts and you simply remove some words and ask the model to complete for the blanks, the only way that the model can do this is if the model has understood some kind of meaning, some kind of distributional patterns of usage of the words. So the idea is to try and learn a function that fits these blanks with the most plausible words. And this is one very nice example of learning, because for doing so, we do not need any label. So we can just take as much text as possible and simply cancel random words and ask the model to autocomplete these blanks. So this is something we can do almost with infinite amount of text, because we simply have to take natural language as examples. One of the first implementations of this intuition is by Mikolov and colleagues in 2013, by this method that you have probably encountered before, which is word-to-vec. And this actually comes in two flavors. One, which is the skip-cam model, in which, given the central word of a sliding window, you try to predict the words in context. Whereas the CBO, which stands for continuous bag of words, is the other way around. So you give as input the words in the context, and you try and predict the word in the center. So these are supposed to be theoretically equivalent. And so a legitimate question now is whether we should prefer counting methods versus predicting methods. So which kind of method tend to perform better? And the funny thing is that Levy and Goldberg back in 2014 proved with a mathematical proof that both methods are actually equivalent. And actually, the next year they carried out many experiments trying to figure out if, notwithstanding the fact that theoretically both methods were equivalent, whether there were some empirical differences. And the results were not clear. So they took a bunch of methods, a bunch of distributional semantic methods. They ran many experiments and they found no clear link. But what they found is that they actually, hyperparameters are responsible for the final performance of the model. So having a model that performs better than another is not simply a matter of the theory which is behind the method, but it's also something which depends from the hyperparameters you choose. So for example, how many words do you choose in the context? Whether you choose only the right context or the left context, both contexts, and so on and so forth. But you know, singular value decomposition and word-to-vec were the two which won the most number of tasks. But we typically prefer word-to-vec over singular value decomposition, because singular value decomposition.
So you mean this SVD of these word matrices?
SVD is actually the matrix factorization of the word-by-word matrix.
Yes, okay.
Yes. And this is exactly the problem. This is exactly why we prefer word-to-vec, because in order for word-to-vec to work, you don't need to create this matrix. So for singular value decomposition, you first have to collect the matrix, then you perform matrix factorization. While word-to-vec is an implicit matrix factorization, is something you do on the fly. So you never have to collect this huge matrix. But apart from these technical differences, both methods are exactly the same. There are some, software packages out there which allow you to create those vectors. One, probably the most famous one is Gensim, which is written in Python. And then there is this problem about, okay, once we have our word embeddings, how could we assess them? How could we tell which set of embedding works better than another? And we typically confront our embeddings through these testing problems. And this started happening when Nikolov and colleagues in their paper of Word2Vec noticed that actually the word embeddings seem to be capturing some regularities in text. So one unexpected behavior of word embeddings is that it appears to be one latent dimension encoding, for example, the shift in gender for words. So for moving from man to woman, uncle to aunt, king to queen, and so on and so forth, happens to be summing one vector to the original noun. And here is another example for plurals that you probably cannot see. But you move from a singular form to the plural form just by adding one that direction, which seems to improve this regularity. And this allows you to perform this analogy test, which is called arithmetic of semantics, in which you can pose this kind of question. So for example, Paris stands to France as Rome stands to Italy. And the funny thing is that if you operate with vectors, like if we were words, then you end up having one vector which is probably very close to the representation of Italy in this case. Okay, so this is how we implement word embeddings. This is how we obtain a matrix of embeddings, which typically is a matrix consistent in as many rows of words and as many columns as columns we have in the vector space, which is typically 100 or 300. This is typically implemented in one data structure, which is called the lookup table, that I will not enter the details. And you typically use this embedded matrix as the first layer in a deep neural model. So this is the typical architecture of any text, whatever deep learning model, in which your very first layer is this lookup table for the word embeddings. So you take the text is transformed into IDs of different tokens or different words. And then you give these IDs to the lookup embedding table, and you transform every single ID into a vector, into an embedding. You typically use here pre-trained values, so something that you have learned outside the model with many data, with as much data as you can. You can find many pre-trained embeddings out there, sometimes even made available for the inventors of the method. So for example, for Word2Vec, we have this Word2Vec trained by Nikolov on all Google News. And for Globe, we have, I think, all Globe vectors trained for all Google News, plus all Wikipedia, and so on and so forth. And from here on, you plug in any kind of deep neural model, be it a feed-forward network, convolutional neural network, recurrent, or transformers. I will not explain the different kinds of networks because this will take too much time, but what I will try to do with the time which is known. Maybe I will take this back again after the coffee break. Okay, this seems like a good moment for the coffee break.
Okay, so we have a coffee break now.
Is there any questions so far? Sorry.
Yeah, sure. Go ahead. Any questions? Well, I guess people are happy. Let's go for the coffee break and try to reconvene in 20 minutes. Okay.
But actually, the supervisor knows the supervisor.
Yeah. Yeah, that's why too. For fine-tuning and then fine-tuning. Yeah, for example, if you want for example, you want to have embedding for fine-tuning configuration, probably the best idea is to take the data set, fine-tune the computer on this, and then it's a nice. The more similar task training task is, the better your investment. Yeah. Actually, it's
Let's start my last
Okay, so we're gonna get started. Before moving forward, do you still have any question related to the previous part? Or should I go on?
Only the name of Python to get the methods.
Yamsing. It's Yamsing, but I don't know why this is not working. This one. Yes. Okay, there are no further questions. During the first part, we moved from the vector space model to the word embedding model, the word embedding space. So we are now going from the neural embedding space to document reading. So how to use these word embeddings in order to build a text classification system. And one of the, not the one of the first attempts, but this is one which has become very relevant in the field, is FastText, who is by Jolin and colleagues, and actually one of the colleagues was Nikolov, who was the inventor of Word2Vec. And FastText is nothing but Word2Vec, but instead of considering sliding windows as context, now we consider entire documents as context. And instead of trying to predict the central word, as in the CBO model, we try to predict the label or the labels in case this is a multi-level classification task. This method also implements many tricks, and actually the paper is called a bag of tricks for efficient text classification, because it puts inside many tricks for rendering the problem much more efficient, much more effective. And one of the tricks they apply is this n-gram encoding style, in which instead of considering single words, you break down the words into character n-grams. So for example, of length 3 or of length 4, so that you do no longer work with words, but with n-grams. As Fabrizio has explained before, this brings the models on resiliency to misspellings. So for example, you can encounter a word like appendicitis or something like that. And even if you have never seen this word during the training phase, you may realize that this is some kind of disease because you have the co-occurrent itis termination, which gives some hints to the model, like this is a disease or something like that. Then there is this model called LEAM, which stands for Label Embedding Attentive Model, in which one and colleagues try to not only embed the words, but also embed the labels. And by embedding the labels, I mean trying to apply the same kind of techniques, so the same kind of distributional semantic models to the labels themselves. And then they try to implement this tensor product, which acts as a, so it computes some terms which in a way reflect how important is every single label for every single term in the document. This is called the attention, the attention weight matrix. And they use these weights here to re-weight the relative importance of every word in order to compute the final representation of the model. And from here, they try and learn any kind of deep learning model. Then we also have multilingual embeddings, and this is one of the most interesting papers. There are many, but this is one of the best papers because this was considered the most important paper of the entire 2017, and it's called Word Translation Without Parallel Data. So the authors managed to align the different word embeddings trained independently on different languages in a single vector space, so that you end up having, so for example, the word cat in English, which is very close to the representation of the word gatto, which is cat in Italian. So this is very interesting from the point of view of our text classification system, because what you can learn from, for example, English directly applies to Italian as well. And they did this kind of alignment by using two kinds of processing, in which the supervised part is this one, which tries to project one part onto the other by means of something which is called the procast alignment. And then they fine-tune this representation by using an unsupervised part, which is based on an adversarial training. I'm not going into the details of what is an adversarial training, but it's something in which you try to fool a discriminator in trying to distinguish whether a randomly picked word comes from, in this case, English or Italian. This is another attempt for devising, for creating word embeddings specifically for text classification, which is by us. And the idea here is to take this result from Levy and Goldberg in 2014, in which they prove that word2vec and a more general family of methods of distributional semantic models can actually be framed along these terms, in which you have that the embedding is any sort of factorization function applied to a vector, which is nothing but this row in our word complex matrix, in which you have, for every dimension, you have some measure, so for example, counts of the co-occurrence of one central word with a word in the context. So this is the theoretical framework that Levy and Goldberg pose. And we use this formalization in order to substitute the words in context by labels. So you end up representing an embedding as a factorization of a vector in which every dimension is some function which measures correlation with one word and every single label. And the interesting thing is that if you take word2vec, for example, which is unsupervised, so it provides general purpose embeddings, and you try and figure out how these embeddings are organized for your task, which in this case is a task of classification. In this example, we are using one dataset, which is called 20 news groups. And I am plotting a bunch of word embeddings, and I use the color for which the word is more strongly correlated. So you can see here that there are some regions in which they seem to be very well clustering, if you want. And if you zoom in, you may realize that there are some words that are very close to each other, like the dietary, vitamin. Also, for example, I cannot really see, protein, metabolic, amino, and so on and so forth. So similar words do stay close to each other, but there is no real global structure. With word class embeddings, is the other way around. If you cluster the embeddings in terms of the correlation with the classes, they create very clean clusters around every class. But if you zoom in into every cluster, you find out that similar words are not that close in the vector space. So for example, Palestinians and Palestine seem to be in opposed regions of the cluster. But word class embeddings were actually proposed to be concatenated to general purpose embeddings. And the thing is that if you combine them together, you end up with a topology of the embedding space, which looks like this. So from the global point of view, there are very clear structures in terms of the classes. And if you zoom in, then the same kind of, semantic similarities between words are reflected as well. So for example, sun, sky, moon, earth, or lunar, or aviation, flight, jets, and so on and so forth. This kind of correlations emerge as well. Okay, to close this part of the presentation, I would like to highlight this shift in the way we typically construct text classification systems from the traditional point of view, in which you depart from static word embeddings, which are embeddings trained outside the model, outside the task, which encode general semantic of the words, and then you try and learn a deep neural architecture to make sense of these embeddings for your specific task. The modern approach is something completely different that I am not going to cover in this lecture, but is something which has to do with transformers. Transformers are these huge models trained outside the model, trained outside the task at hand, but trained with so many texts and so many data and so many GPUs that they already encode a very good prompt of the general usage of language. And so the thing is that if for traditional machine learning, you had a knowledge engineer maybe collaborating with some experts in order to decide for which are the most important features, which is more akin to the part which Fabrizio has covered in his presentation, then what remains is something which we can approximately say that is 10% of the work, because the most important part had to do with choosing the right features. From the static word embeddings, there is a shift in which we depart from word representations which already represent general usage, and this accounts for approximately 50% of the word. Then you have to try a deep neural architecture to end this processing and to make sense of everything. While for transformers, it is the other way around. So we depart from a model which already accounts for, let's say, 90% of the word, because they already provide you with vectors which very well capture the semantic of an entire sentence. And what remains is nothing more than one single linear layer that you put on top of your model and you train with your labels. Okay, this is that I wanted to present for this part. So Fabrizio, will you continue?
Yes.
Okay, I think you have to share your screen.
And probably you have to unshare yours.
Yeah.
Although I think it's not necessary, you can share on top of mine. Try it because I don't find the commands. By the way, is there any question related to this part? Okay. Yes.
Can you see my slides?
Yes.
Okay, great. So let's say, just to recap, let's say up to now we have seen some, let's say, a general part on text classification that started out with what we might call a classic, let's say, a view of text classification based on classic machine learning. And let's say carried out with the second part, the one given by Alejandro, which made a foray, in text classification via more advanced models, essentially based on deep learning and on embeddings. Okay, so now what we're going to do is to make a foray into different tasks that are at the intersection between IR, or at the interface between IR, NLP, data mining, and machine learning, which can be seen as sort of, or have significant overlap with text classification, which may be seen as sort of instantiations of text classification that require text classification technology. And the one I will deal with is authorship analysis. Okay, so what is authorship analysis? So the entire thing, I will start from the notion of trying to spot a fake text. Of course, I mean, there are different notions of what a fake text is. So we are typically very well used to the notion of fake news. Okay, so fake news is a text that reports false facts, sometimes facts that have been purposefully fabricated, and usually are presented as being factually accurate. This is not the notion of fake text I'm looking at. I'm looking at a different notion, which is a text whose author pretends to be a different author, say an author who is a forger. And the latter is actually the meaning I'll be looking at. So the image you are seeing here, this is a portrait of Lorenzo Valla. I don't know if anybody among you remembers him from high school. He was, we might say that he was one of the very early fake text spotters in history. And indeed, he was the philologist who actually basically first realized and then proved that a very famous document called the Donation of Constantine was a fake. So the Donation of Constantine was a document that was meant to let's say, it was sort of signed by the Emperor Constantine, and the Emperor of the Roman Empire. And the document basically says that Emperor Constantine donated to the Pope the Western Roman Empire and kept the Eastern Roman Empire for himself. Okay? So many years, many centuries later, Lorenzo Valla proved this to be a fake, So we are going to look at other documents which are fakes in this sense, and even modern ones. Okay, so here I have an example. Okay, so on a few years ago, the then Italian Prime Minister Matteo Salvini actually publicized an anonymous letter that he said he had received. Okay, so this is a letter that in very uncertain Italian contained threats of various types. Okay, and it was sort of signed by an alleged Albanian. Something say you have 3 Albanians, who are looking on you, and you will be killed. You have been, etc., etc. Several threats of this kind. The interesting fact is that a few days later, there was an Albanian linguist, okay, from the University of Bologna, who argued this to be a forgery. Well, this woman basically said, well, it certainly shows poor knowledge of Italian. but it doesn't, this letter doesn't contain the typical mistakes that Albanian speakers, I mean, speakers that, have Albanian as their L1, as their mother tongue, make when writing in Italian, which is their L2, their second language. She said also that it contained mistakes, that Italians with low proficiency in written Italian typically make, Italians, not Albanians, And it also contained idioms that are, let's say, very Italians and unlikely to be mastered by Albanians, So this is what we might call an attempt at what we might call native language identification, which is a task which is currently carried out computationally, the task of identifying the mother tongue of the author of a text, which is written in a second language. So essentially you have a document written in a certain language, and you want to figure out the mother tongue of that person, be it, a person who has the same mother tongue or different mother tongue. And native language identification is based on the fact that the learners of a second language tend to display a tendency, which is called language transfer or L1 interference, a tendency to transfer structures of their original mother tongue, structures of their so-called L1 linguistic background to the second language, okay? So that can find traces, in that, in the L2 documents, you can find traces of the L1, So the idea is, can we automate native language identification by trying, to detect these traces, And the answer is, of course, a yes. And this is something that I will try to basically show you. So native language identification is just one example of a sort of a galaxy of tasks that is called authorship analysis, computational authorship analysis. And authorship analysis in general, is mainly viewed as the task of predicting, we are back to this terminology, predicting, guessing, hypothesizing, or inferring, predicting the characteristics of the author of a text whose authorship, whose paternity is either unknown or disputed, So authorship analysis, used to be traditionally carried out by linguists, by linguist philologists, via, manual analysis. Manual analysis that included both linguistic analysis and extra-linguistic analysis. So linguistic analysis basically has to do with the analysis of the language traits which are present in the disputed texts. Okay, so for instance, Lorenzo Valla did indeed carry out linguistic analysis. Okay, so he basically argued that one word that was contained in that document, the word satrap, was not used at the time. So the document had to be a fake. The document couldn't have been written in the years in which Emperor Constantine lived. Okay, he also argued that the quality of Latin, in the donation of Constantine was very poor. And it was very unlikely, that a document emanating from the emperor was written in that poor quality. Also, Lorenzo Valla carried out extra-linguistic analysis. So, linguists and philologists carry out extra-linguistic analysis. That means analysis of the concepts expressed in the text, of the facts described in the text, and on the likelihood that a certain author could express those concepts, describe those facts. Okay, so if the document, say, refers, to an event that the presumed author couldn't have possibly known, this is evidence towards the fact that this is a fake. So, linguists and philologists tend to combine linguistic and extra-linguistic analysis. The problem with extralinguistic analysis is that it is very difficult to be carried out by a computer, because this would sort of entail the, let's say, a massive amount of knowledge, of structured knowledge that typically computers don't have, okay, or don't have in formats which are amenable to processing. Okay, so computational means of authorship analysis are actually tend to rely on linguistic analysis. So computational authorship analysis is in general the attempt to perform authorship analysis by computerized means that rest on linguistic and no extralinguistic analysis. Okay, so there are various subtasks here of the authorship analysis, and this table will probably recall you the different types of text classification that we have mentioned at the beginning of today's course. Okay, so some tasks have to do with the dealing. Sometimes have to do with inferring the identity of the author. Okay, so one very classic task in authorship analysis is authorship attribution. So that basically has to do with predicting who among a set of, say, K candidate authors is the most likely author of the text. Okay, so authorship verification is different. It has to do with predicting if a certain candidate author is or is not the author of the text. So here you can clearly see two different instances of classification. So authorship attribution having to do with single label multi-class classification, because you have K candidate classes and you need to pick exactly one, while authorship verification is clearly reminiscent of binary classification. You have to predict if a certain candidate author is or is not. Okay, so it's a binary character. So a third one, same authorship verification, has to do with predicting whether two candidate texts are by the same author or not. Again, a different instantiation of binary classification. There are other tasks in authorship analysis that deal with inferring not the identity, but some characteristics of the author. So for instance, native language identification, we have already mentioned this, so which has to do with predicting the most likely native language of the author of the text out of a set of K candidate native languages. Again, single label, multi-class classification. Gender identification, predicting whether the text was written by a woman or a man. This really, science sounds like science fiction, but something like 20 years ago, a group of Israeli scientists, Moshe Koppel and colleagues, actually proved that gender identification can be performed with, let's say, non-trivial accuracy. So gender identification is indeed on the map of computational authorship analysis tasks. And a task which is very important nowadays is bot detection, say predicting whether the text, which is usually, say, a social media post, was written by a human or a bot. Okay, so especially after the advent of high performance text generation models, such as GPT-3, etc., trying to actually guessing whether the text is really human or not is a non-trivial task. Today, actually, I want to draw some examples from authorship verification, the binary task of predicting if a certain candidate author is or is not the author of the text. And I'm pretty sure that you will be able to map what you see concerning authorship verification to other tasks such as attribution or others. So in general, why is authorship analysis important? There are several applications. Okay, so one is, say, cybersecurity. So that's essentially the prevention of crimes that could be committed with the help of digital means. Okay, so the idea is, there is an anonymous message that transits on the internet, and you want to anonymous message, say, calling people to the holy war, against the West. Okay, and so you want to figure out maybe who was the author of this, maybe, or from which religious group this came, etc. You know. Computational forensics, okay, is also another important branch of application. This has instead to do with the digital analysis of evidence from crimes that have already been committed, you know. So actually, you might wonder who the guy in the picture is. Okay, so the guy in the picture is called the Unabomber. Okay, so he was a famous serial killer who acted in the United States in the 80s and 90s, you know. And the interesting fact, you know, the reason why I'm displaying his photograph here is that he was caught essentially via linguistic analysis, okay? Because he actually, in order at a certain time after killing, say, 20 or more people via explosive letters, okay, so he pledged to stop his killing spree if only major newspapers had published his manifesto. You know, he was a sort of a high, let's say, how could I say, you know, a sort of an extremist and environmentalistic manifesto. Okay, so the major newspapers in the US indeed published this manifesto, you know, until a guy, a reader, actually could spot the guy. He said, you know, this guy is my brother-in-law, you know, because he actually speaks like that. Okay, so he actually was detected via the tweaks, you know, via, you know, specific characteristics of his language. Okay, so as you say, you know, as you see, you know, forensic linguistics indeed, you know, can do for crimes that involve language, you know, such as, you know, threats, blackmail, extortion, you know, what DNA has done for violent crimes, you know. And, you know, a third class of applications is philology, you know, which I'm going to discuss below. You know? I'm going to discuss here. Well, philology has essentially to do with the analysis of texts from cultural heritage. You know? And there are lots of texts from cultural heritage whose author is still either anonymous, you know, or his authorship has been lost in time, you know, due to the passing of time, due to the centuries-old text. So there have been various applications of computational authorship analysis to texts which are of literary or historical values. So the text displayed here is a famous, probably one of the most famous examples of computational authorship analysis. And it is the so-called Federalist Papers. So it was a series of essays which were written in order to support, you know, support the new constitution of the US. Okay, and it was written by a collective authors who collectively signed these papers by the nickname Publius. And at a certain point, you know, something like 50 years ago, philologists tried to figure out, you know, who among these authors had written which essay, you know, and they indeed managed successfully to apply computational authorship analysis techniques. There are several other examples in cultural heritage to which these techniques have been applied. And something which is important to say, you know, is that in a sense, computational authorship analysis is not really meant, you know, in the when it comes to cultural heritage, it's not really meant to replace the work of philologists, but in a sense, it's meant to provide them with new tools, new hypotheses. So philologists are unlikely, you know, to believe a computational authorship analysis system, you know, or to believe its response, you know, on a document which they have maybe studied for ages. Okay, so the interesting fact, you know, for them is if the system provides them with new hypotheses on which to work, And this brings us to a sore point, having to do with text classification and machine learning. And it is the sore point of explainability, So here, in order for a new hypothesis to be of use to a philologist, the machine learning system, the classification system, should not only issue a prediction, say predict that this essay has been written by, say, Hamilton, It should also try to justify this prediction, to explain, why the system believes that Hamilton was the author of this essay, And this, in a sense, clashes with the fact that, machine learning algorithms tend to be black boxes, okay? So tend to issue predictions, but not to be very transparent with respect to, to why they issue certain predictions. So there is active research nowadays in generating explanations from machine learning systems, explanations from classification systems, or also active research in generating, let's say, machine learning algorithms that return classifiers which are inherently transparent. Okay, so where explanations can be inspected. Let's say. So as I was hinting, what we can do is to tackle authorship analysis as a text classification task. What is important really is that what differentiates classification by author from classification by topic. You remember that at the beginning of the course, I had a slide on dimensions of classification. I was speaking of classification by topic, classification by sentiment, classification by author. Okay. So what differentiates classification by author from classification by topic is not the supervised learning method that we could pick. So support vector machine will serve classification by author and classification by topic equally well. It's not the feature selection mechanisms such as mutual information. It's the choice of features. Okay, so the choice of feature, the features that we want to use in order to represent the text is the important key characteristic, for tackling different dimensions of classification. And as usual, if the features have been chosen well, the data items belonging to the same class, which here means the same author, will tend to be close to each other in the vector space. As usual, and here I'm talking in a sort of a classic machine learning view, the choice of the right features is in a sense an art that designer of machine learning based classifiers must master. For authorship analysis, I would also add that unlike for classification by topic, the classic approach to machine learning is still the dominant one. So in a sense, let's say deep learning methods have met with limited success, okay, in authorship analysis. And some of the reasons, for instance, you can see some of the reasons in looking at, say, applications such as in cultural heritage. If I want to classify ancient Latin texts, okay, you cannot find many training documents. And we all know that, deep learning methods tend to be data hungry. So up to now, let's say the classic view of machine learning is still fairly much the dominant one within authorship analysis. And so, in a sense, the choice of the right features, is an important step. And designers of authorship analysis systems, in their choice of features, they tend to look at stilometry. Stilometry is a discipline that studies linguistic style via quantitative means. Okay, so in a sense, the idea of stilometry is to try to make style measurable, in order to detect features, whose measurable impact on a document, could be an indicator of style. Okay, so we are looking at style and we are not looking at content. Okay, so why? Well, because the same author might write about different types of content, okay, different types of topic, So we, in a sense, we made the example of different topics for journalistic news, sports and home news and politics and lifestyle. Well, the same journalists sometimes might write either articles about sport or articles about home news, or articles about politics. So it's not by looking at the content that you are going to detect that you're going to spot a certain author, And so in general, the authorship analysis discipline, authorship analysis scholars have conveyed towards the idea that we should study the style of the author as displayed in a text. Okay, and so that it is the style of the author that gives the author away, not the content he or she speaks of. And because of this, we are trying to analyze style, and because we are doing it computationally, we try to do it in a quantitative way. So typical features which are inspired by stilometry, which are used in authorship analysis, are, say, punctuation symbols. Well, think of classification by topic. Would punctuation symbols be a good feature? Certainly not, because the frequency with which you use a comma is not an indicator of the fact that the article is about sports or is about home news or politics, But, say, punctuation symbols might be an indicator of authorship, say, because certain authors use punctuation symbols very sparingly, while certain other authors, tend to use much more punctuation. Word lengths, say, it is well known that highly educated people tend to use longer words on average, So this is a feature, an interesting feature. Sentence lengths is too, Again, highly educated people tend to use longer sentences, The token word ratio, the token word ratio is the ratio between the number of word occurrences, of a certain word, So some authors tend to repeat the same word all over and over again, while other authors tend to use different synonyms of the same word, Function words, some people, use articles more sparingly than others. Post tags, some people use more adverbs than others, postgrams, sequences of posts, rhythmic features, So recently we did an experiment in trying to understand, the authorship of ancient Latin texts by detecting its musicality, and by detecting its rhythm. And there are also features that are actually indicators of rhythm, such as accent or the length of syllables, etc. So in a sense, the assumption in the use of these features is that the frequency of use of these features tends to fall outside the conscious control of the author, So in a sense, when I write, I tend, to use punctuation in a certain way without, and I will always do it unless I exercise conscious control of it. So because it falls outside the conscious control of the authors, it tends to be author invariant, what people call a digital fingerprint. And it's also hard to copy for someone who might want to forge such a text. Well, the photograph of the guy, Vincent Lutoslavsky, is one of the inventors of stilometry. That's why it's used here. An interesting fact is that stilometry, as I said, stilometry-inspired features would be useless in classification by topic, say punctuation. But content-bearing words tend to be useless in classification by author too, and indeed tend to be as we say, confounding features. Okay, so suppose that I use, we also use, typical bag of words in catching stylometry. The problem is that if we did this, we would tend to capture topic instead of style. And I'll give you an example. Okay, so suppose that I want to train an authorship verifier, that tells me if a certain Latin text was written by Caesar or by Virgil. Well, I would train the system by using texts of Caesar, and the texts of Caesar, tend to be about war reports, because he was a warrior. For Virgil, he has written a lot of text about the beauties of country life, So I would use those training texts. Once I subject, an unlabeled text to a classifier trained like this, well, the peril, is that instead of telling Caesar from Virgil, it would tell, war from country life. So it would not be a classifier by author, but a classifier by topic. Because of these content-bearing features, which are essentially words, but also character engrams, tend to be discarded in authorship analysis. And essentially, while the choice of feature varies across these different dimensions of classification, authorship, topic, etc., the other aspects do not. Okay, so we can use the same feature selection functions, the same learning algorithms, the same evaluation measures. So I'll give you just to finish this part on authorship analysis, a sort of a case study that we recently worked on. So a philologist approached us because he was interested in finding out whether a certain ancient text, the so-called Epistle to Cangrande, was actually written by Dante Alighieri, or was indeed written by a forger. It is a document which is signed by Dante Alighieri, but scholars are divided whether this is a forgery or not. So it's a sort of a long-standing problem in philology. So we tackled it by this is a computational authorship verification problem, because this comes down to deciding whether this is Dante's or not Dante. So how did we go about? So the idea is you fill the binary text classification problem using stylometric features of the type I have listed above. The idea is that you can come up with training documents by Dante, trying to collect all of his production in Latin, because this is written in Latin. Dante was an author who partly wrote in Latin and partly wrote in Florentine vernacular, which is what evolved into Italian. And we also collected negative examples, which were texts by coeval authors, coeval authors A1, AN, and we had to fill the so-called one versus the rest classifier. So one versus the rest is a way of saying that for a binary classifier, you filled one class, which is here called A star, Dante, against all of the other classes, which are all of the other authors, A1 or AN, which act as negative examples for this decision, Dante versus not Dante. And here, we set up this authorship verification system by using the stylometric features, by using SVMs, etc. And we went back to the philology and said, our system, predicts that this epistle was not written by Dante. And the guy said, so what? Well, what we needed to do, is to bring some evidence towards the fact that this system, was reliable. So the idea is that we took, that corpus of texts, and we ran a k-fold cross-validation. K-fold cross-validation means essentially each of those texts, is classified by using other training the other training text. Okay, and so this is a brand of K-fold cross-validation called leave one out. Leave one out means that if you have, say, 300 training documents, you classify one text, by training the system with the other 299 texts. You repeat this by changing the test document every time, so you run 300 experiments, and in this sense, you can compute the accuracy on the entire training set. So in this case, we had very good results. So for instance, here out of 294 examples, essentially we had 11 true positives, 282 true negatives, and we had just one mistake, which was, fairly convincing to our friend philologist. So I'm finishing now by actually noting something. Okay? So you might really notice here that we have very few texts. Okay, so I mean, yesterday you probably saw Nicola Ferro speaking of corpora for the evaluation of ad hoc retrieval, consisting of gazillions of documents. And here we are talking 294 texts, come on. Well, the reason is that when you work on ancient texts, you don't have gazillions of texts. You don't have gazillions of texts whose class texts with known author. So in a sense, in these are settings where you need to make do, with the smaller numbers, and you need to use tools that deliver good quality despite the small numbers, say, of training examples, which, is something that tends to put, deep learning in trouble. Okay, I have now finished, with the part on authorship analysis, and I would like to pass the mic to Alejandro.
Can you stop sharing your screen for it?
Here it is.
Is it okay?
There's a little bit of delay.
Is it? Okay, to conclude this presentation, I'm going to be talking about multilingual text classification. And instead of offering you a survey about multilingual text classification, for reasons of time, we have preferred to focus on one particular approach, which is a joint work with Andrea Esuli and Andrea Pedrotti and Fabrizio Sebastiani, in which we try to devise ways for performing text classification in an effective way. So the idea is that multilingual text classification could come in very different flavors. We can perform multilingual text classification by topic, or by sentiment, or by any among the different orthogonal directions that Fabrizio has mentioned before. So in this presentation, I will be focusing on one particular way for performing simple but effective text classification. And I will be talking about classifiers ensembles, transfer learning, and word embeddedness again. Okay, so in this slide, we have represented by means of some different flags, different corpus in which we have one part which is the training data, and one part which is the test data. So we will assume that every document is written in a finite set of languages that we know in advance. As before, we will be calling this set of features the code frame. And this is a scenario which is common in many multilingual organizations, like for example, any European organization, but also for companies which operate in different countries like Vodafone. Okay, so let's explore the variants in which we can perform this task. The first one is called the monolingual text classification, in which you try and learn one specific classifier for every different language that you then use to classify the documents for this corresponding language. Of course, this solution is suboptimal because there is no chance for this classifier to gain any knowledge about the information which is in the other languages. So of course, we are going to try something better. We are trying to approach the polylingual, sometimes also called multilingual text classification scenario, in which here you leverage all the information which is in English, for example, for classifying all the documents which are in the other languages. And you do this not only for English, but also for Italian, French, Spanish, and so on and so forth. So here the idea is that everybody helps everybody. So the idea is try and improving over the performance that a trivial monolingual classifier, or actually an ensemble of monolingual classifiers would deliver in terms of accuracy. There is also a third scenario, which is typically called the cross-lingual scenario, in which there are some languages for which we do not have any training document at all. So in this case, we are trying to create some classifiers for some languages for which we could otherwise not perform classification at all. And this scenario is typically called zero-shot. In this presentation, we will be focusing on this particular case, polylingual text classification, and in one variant, which is called the few-shot scenario, which for some languages, we may have a comparatively lower number of samples with respect for other languages. Polylingual multi-class text classification could approach many different settings of text classification, like the single label multi-class, in which every document is labeled in terms of one single label, or the multi-label polylingual classification, in which every document can belong to 0, 1, or more than one classes. We will be focusing on multi-label polylingual text classification. Okay, so this is an instance of transfer learning, and in particular, it's an instance of heterogeneous transfer learning. And transfer learning is the branch of computer science in which you try to reuse the information which is available for one source problem in order to perform better or to perform at all in situations in which you don't have any document, any training data for the target domain. And this particular instance is called heterogeneous because in the training side you have documents which are written maybe in different languages or in different vector spaces. So the elements in the source are not even comparable among themselves. And we will be trying to perform this information bottleneck that we have called the funneling system. So the idea here is that we are going to use this metaphor of the funnel in which we are gonna put all the information, all the training data, which are at this stage are still language dependent. And we will try to project them in a common vector space in which the language-dependent differences have been cancelled off. So we will be seeing how to do this and how to do this simply. Okay, so funneling is this architecture in which we have two different levels, in which the first level is the one in which the language dependent information is being processed. And for this, we have represented this kind of black diamonds, which are classifiers in charge of dealing with documents from one specific language. We then have a meta classifier, which receives the information from all of the first tier classifiers. In this case, this information is language independent, and this meta classifier tries to make sense of all this. So how do we do this? So the idea is that we here may have different vector spaces, and this means that we could have different number of rows because we have different documents. We may have different number of columns, but also these columns are not aligned among the different languages. So the idea is that we will try and learn one classifier for every single vector space, so that this classifier returns something which is inherently and natively aligned across languages. And this is interesting because this is learner independent. This architecture is learner independent in the sense that, for example, this diamond here could be a support vector machine, while this diamond here could be, I don't know, logistic regression, and this can be BERT or something like that.
But what are they classifying?
Say it again.
These base classifiers, what they are trained for?
Say it again.
What they are trained for, because they have.
Yes. And of course, you have the same code frame for all the different languages. So we are in this situation in which you have training data for all the documents, and in which you share this common code frame across all the different languages. So for English, you have a training set in which you may have, I don't know, 1,000 documents labeled according to this code frame. Whereas in Italian, you may have different languages, maybe not direct translations of these documents in English, but they are all labeled according to the same code frame. So we are going to exploit this characteristic, that is, we have a common point between all data sets, which are the labels. And so we are going to try and learn these classifiers for every single training set. And as I was saying, for this is also independent of the representation. So you can use the representation that you think works better or best for English, which could be, I don't know, maybe TF-IDF. Whereas for Italian, you could be using bag of words, or by Chinese, you could be using, I don't know, word embeddings. So the idea is that these classifiers all return some information which is aligned. And for this information to be aligned, we have to impose some criteria. The first criteria is, as you mentioned, is the fact that all training data sets are labeled according to the same code frame. But this is not enough, because if you were to simply output classification scores or decision scores, which are the kind of output that most classifiers return, then you may encounter information here which is not directly comparable across different languages. So the idea is that we are going to calibrate these classifiers so that this information are posterior probabilities, because posterior probabilities are completely independent of the language and they have general meaning. So if, for example, we had, I don't know, 100 categories, these would be vectors of 100 components in which every column will speak about the posterior probability of this document belonging to that category. So this makes these representations comparable among each other, and we then can stack them vertically and train a meta classifier. Okay, so the idea is that the funneling metaphor puts vectors, put information which lies in completely heterogeneous and different vector spaces into one single vector space, which is common for all the document, because all the language dependent part has been cancelled. So for example, here you have, I don't know, for Spanish you have dimensions that could be words in Spanish, while here, after the funneling, you have dimensions which speak about the posterior probability for belonging to the first category, the second category, the third categories, and so on and so forth. So you will be working in a vector space which has as many dimensions as classes or categories you have. Of course, in order for this to work, the meta classifier should be working with information which is well aligned across different languages. And in case you are working with classifiers that return decision scores which are completely different among each other, we can apply the calibration, the posterior probabilities calibration, which is something that Fabrizio has explained before, but maybe I will devote some words about it. So calibration, what does it mean? Calibration means transforming any real valued signal into the 0-1 interval so that this new value has a probability, an interpretation in terms of posterior probabilities. And more precisely, this is a very complicated formula that can be summarized with this sentence. Out of all documents for which the classifier says, for example, 0.9, out of all these documents, 90% actually belong to this category. If your classifier satisfies this probability, property, then we say that the classifier is well calibrated. There are many classifiers that are natively calibrated. So, for example, logistic regression is one such example. But there are other classifiers, like, for example, naive Bayes, which return posterior probabilities, but, however, are not considered to be well calibrated. So you can take, for example, naive Bayes, calibrating the outputs of naive Bayes, and then you can use safely these classifiers, one of the classifiers in your ensemble, because the outputs will be well aligned across the different languages. Okay, so we have actually experimented with two different variants of this idea. One, which is called the FAN-TAC, which stands for train and test. And another one, which is called FAN-K4 cross-validation. So the idea is that we take the training set in FAN-TAC, we take the training set, we train a classifier out of this training set, and we reclassify all the documents in the training set in order to obtain these vectors of posterior probabilities. Then with these posterior probabilities and all other posterior probabilities that go from the different learners, we stack them together and train the meta classifier. This presents one particular problem, which is the fact that for training, these posterior probabilities will be overconfigured. So they will be of higher quality with respect to when we deploy the system in test. For the simple fact that the meta classifier will be trained with posterior probabilities that came from the same document for which the first tier classifier has been trained. So the meta classifier is receiving posterior probabilities that will likely be of higher quality. So in order to solve for this, it is theoretically better to take the training sets and generate posterior probabilities by means of K4 cross-validation. So you perform K rounds of training and test in which you leave outside the training one of the folds in time, and you create the posterior probabilities for all the examples, but in a way that one vector, one posterior probability has never concurred in the training or generated. Of course, this is computationally more costly, but it solves this problem I mentioned before. Actually, K4 cross-validation has another problem, which is the fact that the final classifier has been trained with less data because all the first tier classifier have not seen all the information which was available to them. Okay, so at this point, one could wonder if funneling is actually an instantiation of something which is called in literature as stack generalization by Wolper. Well, the answer is no. It is not a generalization of stack generalization for the simple fact that stack generalization is not an heterogeneous system. Stack generalization assumes all the documents to be written in the same vector space. But aside from this, it assumes that the classifiers are of different nature. So they are all working with the same elements. And the idea is combining the outputs that different classifiers would produce in order to stack them horizontally, so that the meta classifier learns from the output generated by differently characterized learners. And finally, this is not the case because we are stacking the information vertically. So we are learning from different sources of information that could be different documents, and so are completely two different things, even though both approaches are based on the idea of ensembles. Okay, some experiments we have carried out using two data sets which are publicly available, which are ESSIR2 and ESSIR1 and ESSIR2, which consists of comparable documents. Comparable means that documents belonging to different languages may not be direct translations from them all, but certainly speaks about similar things. This is a data set consisting of news written in different languages, and we have nine languages and 73 classes. We also have JRC APIs, which is instead a parallel corpus, which are laws from the European Parliament, written in 11 languages, and we took the most populated 300 categories. As the learner, we use for the first tier support vector machines with linear kernels because we use a representation based on TF-IDF. And we know from literature that linear kernels with support vector machines tend to work very well in sparse and high dimensional spaces. But we also know from literature that radial basis functions tend to work better when the space is low dimensionality and dense. So for the meta classifier, because this meta classifier will be working with dense representation of 73 dimensions or 300 dimensions. It's typically better to use one of these more sophisticated kernels. Okay, we have some baselines that I am not going to explain in detail, and we will evaluate the classification accuracy in terms of F1, which is the measure that Fabrizio has explained before. And we also added this K evaluation measure. This is which is a proxy of balanced accuracy. Okay, so these are the results. Oops. In which there are two emerging facts. So the first one, okay, so first of all, we are representing the relative improvement with respect to the monolingual baseline. So for example, this bar being below 0 means that the performance for Danish of this method works approximately 10% better than the corresponding monolingual classifier trained and test in Danish. Okay. So one of the facts that emerge from this figure is that both variants of funneling are the only methods out of the baselines which systematically improve over the monolingual classification. And the other fact is that FANTAT, which is the train and test variant, tends to perform systematically better than the variant in which we perform K4 cross-validation. And this is good news because FANTAT is computationally lighter. These are some numerical results that are not particularly interesting. And so in this experiment, we tried and figure out where exactly is what exactly is funneling learning. So is funneling learning about the stochastic dependencies that exist among the different classes, because this is a multi-label code frame, or is funneling improving over the monolingual classification because it's taking advantage of the different languages which are in the training sets. So we have performed 2 experiments doing Bayesian studies. So for example, in this experiment, we are testing monolingual classification with funneling. So the idea is that there is only one language for which we train and test using funneling, but in which this 2-tier architecture is being used. And you see that there is a huge improvement with respect to the naive binary monolingual classification. Although the improvement is much higher in the case in which we work with binary classification. So these are, for example, in the case of the ESSIR quiz, these are 300 experiments in which for every experiment, you only consider one of the categories, but you consider the multilingual component. So the improvement is much higher than with respect to the multi-label monolingual classification, meaning that funneling is actually improving more about the multilingual facet of the dataset than to the multi-label facet of the dataset. Okay, so at this point, we ask ourselves if we could move further. And the idea is if we could come out with different representations which are more sophisticated than these posterior probabilities, and whether these could bring additional advantages, additional improvements in performance. And the answer, of course, is yes, otherwise I would not be speaking about this. So the thing is that we will try different mechanisms to generate document representations, provided that these document representations are already aligned across languages. And for doing so, we are going to exploit different correlations beyond those that we have already explored. So in funneling, we were exploring class-class correlations because the meta classifier was trained on vectors of posterior probability. So it's trying to make sense of the correlations, stochastic correlations that could exist in the vector of posterior probabilities. So the idea is that we will try to bring into bear the word class correlations and the word correlations. And the intuition is that we will be using different and language-aligned views of the documents that encode these particular correlations. So we will be generalizing over the concept of posterior probabilities towards view-generating functions, which are functions outputting representations of documents, so that every column has exactly the same meaning as the same column for another language. Okay, so that we can then stack vertically all this information and still try and learn one metaclassifier. So we have experimented with 3 different view generator functions, which are in the first case are those news vectors that I have presented before. So these are embeddings which have been aligned by means of a post-processing technique, so that every word, every translation equivalent word across different languages is expected to have very similar representations across the languages. So if we create document embeddings out of these word embeddings, which are already aligned, we should expect this vector to be aligned, to share meaning with the vector space produced in other languages. We then use the word class embeddings that I have presented before, in which every embedding encodes the correlation between word and class, words and classes. And there is no need to post-process these vectors because they are born aligned, because the categories are the same, because we are using the same code frame for the same training data sets. So any representation you could create out of word class embeddings happen to be natively aligned across different languages. And finally, we use BERT. And in particular, we use multilingual BERT, which is actually BERT, but trained on many languages, many different languages, but the architecture is the same. It has only been exposed to text written in different languages. Okay, so these are the results. I am not going to enter much into the detail, but this is the previous fund, what we have called FunTet before. And you know, BERT was proposed after we have proposed funneling. BERT alone works much better than funneling. These are experiments in which we run generalized funneling with only one view generator function. X stands for the posterior probabilities, M stands for news embeddings, W stands for word class embeddings, and B stands for BERT. And you know, most of these configurations work better than the original funneling. Actually, all configurations, sometimes but this one, work better than funneling, the original one. But in particular, generalized funneling with BERT tend to work particularly well. Although the best configuration overall is one in which BERT concurs with other view generator functions, in particular with posterior probabilities and muses embeddings. Although this configuration in which we use all four different view generator functions work better than BERT alone and work much better than funneling alone. Okay, so where can we go from here? So the idea is that we have tackled the multilingual problem, but there are many other instances of heterogeneous transfer learning. So for example, one instance of heterogeneous transfer learning is the multimodal, in which you could take different training sets, in which one training set is about, for example, text, another training set is about videos or images or audio and so on and so forth. So you try to put all this information, which is originally heterogeneous, into the funnel so that you cancel out of all this media dependent information. And so you can use the same architecture, provided that you come with well-designed view generator functions. Of course, we could try also with different code frames, because this is the cornerstone of our method, is the fact that we know that the different training sets are all labeled according to the same code frame. So it would be interesting to see how to approach a situation in which you have different code frames. For example, you don't have any positive example for one of the languages or one of the media, and so on and so forth. And zero-shot classification is something in which we have actually worked. And but I am not going to enter the details. But you can also use funneling for zero-shot classification. Yeah, I'm not going to do the details. Okay, so that's all for my part. Is there any question? No? Questions?
If not, I guess Alejandro will still be around for a couple of.
Well, actually, we have so much material that I think it's better to end here, because I mean the other presentations are worth more than half an hour. So, I mean, for me, it's the same. One can be here. Okay, do you want to, Fabrizio, are you around?
Yes, I am around.
Because I think maybe it's better if you present the sentiment analysis part. I mean, at this point, we could choose with whether to present sentiment analysis or quantification. And so it's my impression that quantification would take much longer.
I apologize, but I have to rush now. Isn't it the end of the lesson now?
Yeah.
Because I may have mistimed things because I have a dentist appointment now. So I may have mistyped things. Wasn't this meant to finish at 5:30?
Yes.
Yes.
Yeah. So I apologize, but I cannot.
Okay, so then it's up to you. You want to go on with text quantification or stop here? I mean, to me, it's not good.
So who wants to see, well,
Fascinating world of text.
some details about text quantification? The problem of figuring out how many examples of a given class you have in the data set. Okay, so I think people are tired. So you're still going to be around for a couple of days, right?
Yes.
Okay, so if you guys have questions or additional comments about this lecture, you can still talk to Alejandro. I'm sure Fabrizio can also answer any questions that you have by email.
Yes, I really apologize for having to leave now, but I do have to leave.
Okay, any questions?
Thank you very much for your attention.
Let's take the speakers again. Okay, and I guess this is it for today. Reconvene here tomorrow morning, okay, for 2 additional lectures. Okay, see you tomorrow.
And the automatic description will not be that good as is this person was related. If you know any papers.
For sure, this is I mean, knowing which is the natural determining the molecule or somehow like switch the best select the best molecule before yeah.
I was just wondering if you could like fix some of the automatic mistakes that just.
We generalize and generalize also speech. So there are techniques and I don't know in particular this whole sense. Certainly there are some issues
Yes.
okay, write me an email.
Yeah, I can write you an email. Thank you very much.
Come volevi fare?
So I think I included Ricardo as well, although I'm not sure if he's joining or working from his hotel. I don't know, so I don't have his phone number, I just sent him an email as well, and he still hasn't replied, so I'm not sure.
Perfect, thank you.
I think we didn't forget him, so I'm not sure if Martin was leaving today or not. He was leaving today, and the student was leaving as well, probably. I think I included him. Yeah. Well, I don't think I forgot anyone.
Okay, see you.
Bye-bye.
Informazione spazio, come si dice, locale, nel senso che se non importa dove sei andato, te lo trova, se qua, questo si può valere anche per nel senso che nei documenti
Alexander, do you mind if I turn this off?
Yeah, sure. Yeah, you have to keep this.
Yeah, I will save to remove it.
Ci sono 5 espressioni